welcome everybody to Benjamin Böhme's PhD thesis defense. So I'm here sort of to welcome you, to tell you, but most importantly to tell you what the rules of the game are, right? So Benjamin is going to defend his thesis. He has 45 minutes to talk about it. After the 45 minutes, you guys will be allowed to ask questions, okay? And then you will also be allowed to leave. When this is over, when people who are done left, then the important people take over. And the important people are the committee members. So we have John Greenlees sitting here. We have Andrew Blomberg sitting here, and then Lars Hesselholt, who is chairing the committee. Okay, so these three people are going to ask the important questions later. And then there's one more semi-important person here, but playing no role whatsoever.
The person who opens the champagne.
Who opens the champagne, maybe. Jesper Brodel, who was the thesis advisor. Okay? And one extra role I am told I have is to make sure that everything happens in a dignified way. And then lastly, I'd like to say hello to Copenhagen, who is online watching the defense. Benjamin, the word is yours.
Thank you for the kind introduction. Thank you all for coming today.
You're the enforcer, Natalie.
Sorry?
You're the enforcer.
I'm the enforcer, yes.
I would like to thank Andrew especially for coming here across the ocean just to be here today. Okay. So we have a standard opening line for seminar talks. Jimmy, your final piece. And I'm interested in G-equivariant homotopy theory, so G-cohomology theories, G-spectra, and I'm especially interested in multiplicative phenomena. And those have gotten a lot of interest in the wake of the solution by Hill, Hopkins, and Ravenel of the Cavalier-Variant 1 problem. And we still don't know everything about multiplicative phenomena, even in the most fundamental examples. And I want to shed a little bit more light on that today. And my goal for this talk is the following. I would like to describe the multiplicative structures on certain spectra that have been around for a long time already, namely the idempotent summons of some of our favorite examples of G-spectra. So that is the G-equivariant sphere spectrum, and then complex topological K-theory, G-equivariant, and the same for real K-theory. So I guess my job for the next 44 minutes is twofold. I have to tell you what I mean by idempotent summon, because it might not be obvious. And I have to convince you that studying multiplicative structures on these is actually a subtle and interesting question. And then hopefully give some answers to these questions. All right, so let's start with the idempotent summons. So, of course, classically, if you start with a discrete commutative ring, R, and say you're given a decomposition of the unit element 1 into a finite number of idempotent elements, then you see very easily that you get a decomposition of R as a sum of the ideals generated by the elements EI. And then since these elements are idempotent, it's also easy to see that this is a commutative ring again, and that what you've actually done is decompose R into a bunch of localizations at these idempotent elements. And then of course you all know that the localization of a commutative ring will be a commutative ring again. So this is all very easy. You can do similar things for spectra. is a G-equivariant ring spectrum. And right now I'm going to be sloppy about what that means, and later on I will be a little bit more precise. Say we're given a decomposition of 1 into a sum of idempotents in the G-equivariant homotopy position R in degree 0. And we can do the same thing. And we get a decomposition up to homotopy, let's say, of R as a product of certain localizations at these elements EI in the world of spectra. And here, by this localizations, I really mean take the coelement that you know from commutative algebra and make it a homotopy coelement. So with multiplication maps by EI, and you take the sequential homotopy coelement. And in particular, since homotopy groups and sequential homotopy coelements like each other, this will recover the localization on the level of homotopy groups. Okay, so far so good. Now let's look at these examples. This figure and K theory. So recall that the G-equivariant homotopy groups of the G-equivariant sphere spectrum can be identified with A of G, the Burnside ring of the group G. So this is the Grothendieck ring of the category of finite G sets, with addition multiplication given by disjoint union and Cartesian product. And this identification is due to C. And then for K theory, let me just write it down in the complex case. It's similar in the real case. Binaural KG is the complex representation ring of G. And I guess this is by construction. So what we need to do in order to get this machinery of idempotent splittings running is to find the idempotent elements in the Burnside ring and the complex representation ring. We can do this in a movie before. For the Burnside ring, this is a theorem due to Dress, and it says the following. If we look at the primitive idempotent elements, so only those that you cannot decompose as a sum of other idempotents in A of G, and then there will also be a local version for the T local Burnside ring, and I also want to write down a version for the rationalized Burnside ring. And this bijects with certain group theoretical objects, namely conjugacy classes of, in the integral case, it will be perfect subgroups. Perfect subgroups, say L and P. And then in the P local case, it will be P perfect subgroups. And in the rational case, it will be conjugacy classes of all subgroups with no extra conditions. P perfect might not be standard term. We can give a quick definition. L is P perfect if there does not exist a surjection from L to Z mod P. There are other factorizations, but I think this is the easiest one to write down. Okay, so in particular, using what I wrote up there, we get a decomposition of the G-equivariant sphere spectrum into idempotent summons given by these elements EL. Let's call them EL, and this corresponds to L.
What is P?
Well, P can be any prime. Okay, we should do something similar for the complex representation ring. And there, turns out that it's well known that if you look at RUG integrally, and this is connected, by which I mean its primordial spectrum is connected, or in other words, the elements 0 and 1 are the only idempotents. And you don't get Galois splitting because the splitting is trivial. This is bad news, but you could ask about the splitting that exists maybe p-locally or rationally. And I tried to find this in the literature, and I spent like 2 weeks just reading rep theory papers, and I couldn't find it. So I had to do it myself. I think there was one more thing I wanted to say here. Oh yeah. So first of all, state this. So of course there's a unit map from the sphere spectrum to KUG. And on homotopy groups, this induces a map from the Burnside ring to the complex representation ring, which is a very familiar map. I like to call it LIN, a linearization map. So all it does is it takes the class of some finite G set X and sends this to the G representation with basis X. Just linearizes the finite G set X. And then the other thing that's well known is that Lin applied to one of these elements EL that are idempotents in the Burnside ring will always be 0 unless as a cyclic just kills off all the ones that correspond to non-cyclic subgroups. So my first result that I would like to present today is the following. It's a classification of the idempotents in the local versions of RUG. So the elements Lin apply to BC for C. Okay, so in the P-local case it will be P-perfect cyclic, and in the rational case it will be any cyclic subgroup. Precisely the primitive idempotent elements of the representation, primitive idempotents of RUG, either P-locally or rationally. This is the classification. If you think about it for a second and try to write this down in the same way as here in the integral case, then this remains true actually, because we would say that the idempotents in RUG are the cyclic perfect subgroups. There's only one is the trivial group. It's exactly the statement that RUG is made. Okay.
So P-perfect cyclic is just cyclic of prime to P order?
Yes, exactly.
Is E sub L G mod L?
No, it's much more difficult. I think you can't even write it with only positive coefficients in the standard case. It's much more difficult. Okay, this is what I want to say about these idempotents. Now we have these splittings. So the next step is to talk about equivariant ring spectra. We have to work cumulative. Okay, let's forget about equivariant just for a second and just recall what a cumulative ring spectrum might be. So I shouldn't call this definition, so put some quotation marks here, just to give the idea. As you all know what an infinity ring spectrum is, you just want to write it down in a nice way and then generalize. An infinity ring spectrum R has multiplication maps. Form n smash copies of R. They are unital and associative and commutative up to coherent by the homotopy. So I want to write down the sentence again later on, so let's just call it nice for now. There's multiplication maps that are nice, and then later on when I say nice, it means all of these properties up to coherent higher homotopy.
Does up to coherent higher homotopy apply to all three of those adjectives? Unital, associative, and commutative, or just the last one?
Good question. I guess it depends on how you make it precise.
Well, I'm asking you.
I guess what I have in mind is an E-infinity opera acting on some algebra. But I don't really want to make it precise because I would have to talk about equivariant operas, and I'm trying to avoid that today. There's a bigger one than that. So let's just copy this definition and make an equivariant. A naive G-infinity ring spectrum R has multiplication maps, has for all subgroups H and G H equivariant multiplication maps. Just restrict the R, we want to say compatible, down to H, restrict down to H, and then multiply this. Very nice. Now, we can ask whether this is the right notion of an equivariant ring or not. Let's recall that here in this setting, the fact that once you make this notion precise, then you can talk about some reasonable category of E-infinity rings, maybe algebras over some operas, and they should be equivalent as a homotopy theory to commutative monoids in some nice model of spectra. Let's say orthogonal spectra for definiteness. And then you can ask what happens here. And here it turns out that once you set up a category of naive infinity rings and you ask what is equivalent to commutative monoids in our standard model of orthogonal G-spectra, and that's not true. So one has to be a bit careful here because Blumberg and Hill found a way to sort of tweak this mesh product just a little bit so that the statement becomes true. But when we say orthogonal G-spectra, we typically mean this mesh product, but this is not true. Let's try again. This time we're going to replace naive with genuine, because this is always what does the trick. Genuine G in infinity ring R as for all H and G and all finite H sets, say T, H equivariant multiplication maps of the form smash over T, restrict down to T, the spectrum R, and then send it to the restriction onto R again. And these maps should be nice. And I certainly have to explain this notation. Where this symbol interpreted in different ways. So if T is trivial, just a set of points with no G action, no H action, then it should be just interpreted in the way we've seen before, as restricting out to H and smashing the usual way, just a smash product. If T is just a single orbit, so H mod K, K is some subgroup of H. Is there something wrong with the light here? It's like it's always going
It's
on.
not
and on.
wrong, it's where the blackboard is, because if there was a beamer, it would go out and this is down and up. So I think if you could switch on the main lights, then maybe it's not so disturbing anymore.
It's okay, it's just wondering.
I think this is on purpose.
If T is a single orbit, it should be the Hill-Hopkins Ravelot norm of the restriction of K of R. And in general, you can extend these two and say if T can be decomposed to this John union, then just decomposed in the obvious way. T2 like this. Alright. And maybe I should say that in the middle case, this functor is the HHR norm functor. So for those of you who haven't seen it before, think of tensor induction, as you know it from representation theory maybe, but then with respect to the smash product rather than the tensor product. So it's just H mod K worth copies of whatever you put here smashed together, but then the action is twisted by the H action on the index and set H mod K. Yep.
When you write res sub T, are you claiming that also the restriction depends on what T is, like how you restrict on it?
Well, so
Or I guess I'm asking, what is res sub T?
for example, in this
without the
case, I
smash?
want to restrict onto K to make sense with this functor, because this functor should take K spectra to H spectra, and res T is my shorthand for restrictor to the right category where it makes sense. I don't know of a better way to write this down. I think if T is some disjoint union of H sets, you can set up some category on the product of these categories of spectra and so on. There's a little bit about this in the appendices of HHR. Okay. Let's do some examples. Here's the obvious example you might have anticipated. The spectra that we're talking about today are genuine E infinity. So for the sphere spectrum, I guess it's fair to say that this is sort of a construction of category of G-spectra and the smash product. To get the right ring structures on K theory is a bit more difficult. There's a paper by Joachim where he constructs these structures from operator theory, from Clifford algebras, C-star algebras. Okay, let's do a non-example. This is a theorem uses pure. I think it's from '96. He found out that the K construction, one studied by Greenlees in May, preserves an E version of the infinity rings. But it does not preserve the genuine version. Then I have a second non-example. So along the lines of how McCure proved this, Hill and Hopkins came up with an interesting example. you look at the map from 0 into the reduced regular representation of G, remember that G is a finite group, and this map defines a class, call it alpha maybe, in G-equivariant homotopy of the sphere, and this will live in degree minus rho G twiddle, such that if you form the localization, which just inverse alpha, remember that this is just a sequential homotopy colimit along multiplication by alpha, such that this spectrum does not admit any. I have to introduce a notation here. Let's call this map n sub t. Let's call it the norm map. So that it can refer to this kind of structure. Does not admit any norm map. And g mod h if h is a proper subgroup. So this is a localization functor that destroys norm maps. It destroys a certain part of the equivariant ring structure. And you can ask, what happens in general for localization? What part of the ring structure is preserved? What part is destroyed? And I would like to state a result by Hill and Hopkins that deals with this kind of problem.
Did you say rho tilde means reduced regular representation?
Sorry, what was that?
Did you say that, does that rho tilde mean reduced regular
It's the reduced regular representation, yes. It's the one that doesn't have fixed points, which is crucial. So in order to state this result, use Hill and Hopkins, need a little bit more notation. We need to talk about the
Do you
induced
want
structure.
to say why it doesn't admit any rules?
I can. Maybe ask it again at the end, and then I'll say a bit about it. We'll talk about the induced structure and homotopy groups. Since it just got interrupted by Greenleaf's, I don't know its name. There's the Greenleaf's main one that was actually studied before this whole theory of the Hopkins-Ravenel came up. But if you, what you can obtain this normal homotopy groups from the one above as follows. You get induced maps of this shape. You induce up from the subgroup H to G. And if you have a class here, so this is a map F. And this operation just applies the, which is our norm, is the one G mod H, to this map. And it turns out that this is actually the G-sphere spectrum. And here you can internalize this operation by applying the above norm multiplication. And then you have to find an operation on homotopy groups. And now the fundamental insight to the Hill and Hopkins. Following. Let's say we start with a genuine G infinity ring, and we have some element X in zero homotopy that we don't like. We would like to invert it to make it disappear. Then localization still admits a norm for H1K, by which I mean that if you form the correct diagrams, I'm suppressing restrictions right now. So you have norm here. You're asking, can I get a norm here? Is that possible? And the statement is, it's possible to get an induced norm in the localization that's compatible with the old one, if and only if a certain condition holds. If and only if the Greenlee's main norm of x divides the power of the element x restricted onto h in H equivariant homotopy. This is the condition, and maybe a nice way to rephrase this is saying that, of course, classically, if you invert elements in commutative rings, you implicitly invert all powers of these elements. And to get the right notion in equivariant homotopy, you have to make sure that you invert all equivariant powers, which are these elements. Right. And now it makes sense to talk about more general notions of equivariant rings. Let's give another one be the definition. One right this. An infinity ring spectrum. N stands for norms. Has norms NT. T is again a finite H set. And H is a subgroup. For a specified collection of these T. So this collection should be reasonable. I'm not going to write down what that means, but it should at least include all the trivial ones, where H acts trivially. So in the case we just take the collection such that all T are trivial, we recover the notion of the naive G-equivariant ring spectrum. If you allow all T, you get the genuine version, but this notion of n infinity interpolates between those two. You can get other structures parameterized by these choices of T that you allow, or T that you require norms for. And then this leads to a whole coset of possible ring structures. Coset of equivariant inducible ring structures.
Excuse me, is there a missing word between specified and of? A specified
It
collection.
should keep, thank you, collection. This coset has a unique minimal element, which is the naive structure. It has a unique maximal element, which is the genuine one. But then, depending on what your group G looks like, there can be many different structures in between.
When you say trivial ones, you mean ones with trivial actions?
Exactly. Now that we have developed the language to talk about Equivariant ring structures, and we've seen the idempotent summons, we can put all of this together. And go to the next section, which I call main results. a little bit close to curtains maybe, so that there's no sun in the blackboard here. I think if you pull those ropes somewhere. Oh, that's fantastic. That's enough. Thank you very much. This is my first main result. Let's fix some nested subgroups K in H and G and ask whether there are norm maps for the p-local sphere spectrum. Then p-local sphere spectrum with the idempotent given by some subgroup L. I guess here L is p-perfect. In this localization, this idempotent summon admits norm map up from K to H, even only if the following group theoretical condition holds. For all L prime that you can find, sitting inside H, such that L prime is conjugate in G to L. L prime has to sit inside K. And then it's the same thing for K theory.
What did you say that L prime was?
Sorry?
What did you say that L prime is? For all L prime.
L prime is a subgroup of H.
That's the only thing.
Yeah. And you want it to be conjugate to L. And then any of those conjugate copies has to sit inside the smaller subgroup that you're norming up from. Okay, let's do the same for K theory. Now we have to restrict to cyclic subgroups to make sense of this. So let's say C is P perfect, or just P prime as that's not pointed out, and cyclic. Then KG C localized, and then you invert EC. Admits norm from K to H. If you know the, and it turns out it's exactly the same condition, so I just copied it for all C prime and H, such that C prime is conjugate to C. C prime is contained in K. So this is the p-local version. And then let me just remark that the same is true integrally for the sphere, and it's true rationally in both cases. So it's true for the rationalized sphere, and the same conditions also hold for the for K theory. And also for real K theory, the same results hold without changes. Then what's more is that there are algebraic counterparts of this. So algebraically, the same as about holds for multiplicative induction on the associated homotopy Mackey functors. So on the Mackey functors given by the Brunside ring, so A blank, and then by the representation rings, the complex and the real version, and then also for the localizations of these. When did we start exactly? Still 5 minutes left. So maybe one easy corollary of these main results. So you can have which of these idempotent summons are actually genuine G infinity, which are the ones where you don't do structure. You can obtain a description very easily from this. equivalent. The group L or C or whatever you started with is trivial. And then since the P-local sphere with EL inverted is genuine G infinity, and second case theory the summon given by C is genuine G infinity. It's sort of a very disappointing result that always only one of those summons is G infinity again. And I should say that also here the same holds for other local versions and so on in the equifunctors. And I should give proper credit because in the special case of the sphere P locally, this is actually due to, yes, sure. I think it's still unpublished, but I guess it's coming soon. So yeah. I prepared one small example to show you these results in action. I'm going to do this on the blackboard. What we're going to do is to group sigma 3, the symmetric group on 3 letters. And we're going to work 3 locally because sigma 3 doesn't have perfect subgroups. But it does have a lot of 3 perfect subgroups. Example. It's easy to see that the 3 perfect subgroups of sigma 3 up to conjugation are the trivial group. Certainly doesn't subject onto Z13. Then the conjugacy class of the groups of order 2 and the whole group. Because the order 2 subgroups are not normal. So we get 3 idempotents. So what I'm going to write down is, I'm going to write down the subgroup letters of sigma 3 here. Just like this. These are the inclusions of subgroups. And we're going to write down the Burnside ring functor locally. And I don't know how to write down all these modules in a nice way, so I'm just going to write down the ranks of these modules over Z3. Sorry, the 3 local integers, I mean. This is rank 4. The ones in the middle are rank 2. And this is rank 1. And now, solid arrows indicate norm maps. This guy is the homotopy groups of a genuine G infinity ring spectrum, so we have all the norm maps here. And now this thing splits into 3 summons, 3 idempotent summons, given by these subgroups. So here the one for E1 inverted. Here we have EC2 inverted. And here E sigma 3 inverted. And then these look as follows. This is rank 2, rank 1, rank 1. All the other ones here die. These 2 die. This is rank 1. There might be a norm map here, we don't know. Here there's a norm map for trivial reasons. Just the 0 map. The 0 map between 0 rings satisfies everything you want to. And here, let's see. This should be rank 2, this should be rank 1. Somebody check that these numbers add up to those. The corollary set, in the case of the trivial subgroup, we get all the norm maps again. We get the whole genuine structure again. So here you can just safely write down solid arrows everywhere. And the only thing we have to check that we actually need these conditions for that I wrote down is this arrow, this hypothetical arrow. Because you can't go from 0 to a non-trivial ring by some sort of multiplicative map, some power map, it's just impossible. But there might be a map here. If you check the conditions, turns out that there isn't. So this is actually the smallest, non-obvious example where you do some more structure than you might have thought. I think I'm going to stop here. Thank you very much.
Okay, so we're ready for the next stage in the program, which is questions from the audience.
So on this list of your results, you don't seem to have integral A theory then?
Oh, because there's no splitting, because RUG is connected.
So in the cases where you prove existence results of homotopic coherence up to a certain level, do your methods give information about the space of structures? Other that's non-empty?
What do you mean exactly?
Well, there's probably a space of so-and-so coherent multiplications, and you could wonder, you're showing it's not empty, but is it connected? Is it contractible?
I guess you would look at these G spaces in the operate that give the structure, and then think about what fixed points are non-empty and what fixed points are contractible. All of the fixed points will either be contractible spaces or non-equivariantly contractible spaces or empty. I guess this is what you're asking for. Maybe.
So what is your E1 in sigma 3?
How do you specify elements in the Burnside ring?
I mean, as a G set, as a formal sum of G set.
The virtual G set.
Yeah, as a virtual G set.
I don't know from the top of my head, but I can write down the marks if you like. So in this case, the Burnside ring of sigma 3 you can embed into C generated with a trivial proof plus C2 plus A3 plus sigma 3. The map is given by taking fixed points and counting cardinality. And in this case, E1 E1 goes to 1, 0, 1, 0. You know that there can only be zeros and ones here because it's an idempotent. This is what happens. It's also not hard to figure out what the other ones do. This one just has a 1 here, and the last one has a 1 here. And you can see that they add up to 1.
More questions? Yeah.
So if you have these results for the sphere, do they imply them for all outbursts over the sphere? I mean,
You
you
can
have
all-
basically the same results for K theory as you did for the sphere.
Well, that's very special. That's the fact that these idempotents are related by this map that I called Lin. Showing that if you have an idempotent here, it either goes to 0 or it goes to a primitive idempotent. So you have to check these conditions that Hill and Hopkins suggested. You have to do some computations. But this map is compatible with all the structure inside. So whatever relations hold here, you can just pull back and check them there. This is why you get the same result in both cases. But in general, for an arbitrary pair of these rings or Mackey functors or whatever, of course an idempotent goes to an idempotent, but it need not be primitive anymore. It might split up. Even in this case, if you pass from here to something like RUG, and then you tensor up to some splitting field or whatever, some finite extension of Q, then in here these elements will split. And then you can't pull back these computations to the Burnside ring anymore. Maybe to talk about it a little bit more if that was too
Afterwards,
unclear.
More questions? No? Well, I think we can thank Benjamin for his talk at least. We take a 3 minutes break or 5 minutes break.
People are allowed to stay if they want, but they're also allowed to. I think we'll only have the champagne after we have the.
I think no drinking before.
No drinking before.
There is one downstairs.
So,
Just all that information.
There are very simple notes here. I'm confident there are enough references available.
Is it okay if I stay?
Sure.
What do you prefer?
No, I prefer this.
I expected that everybody would say.
I'm just hiding in the back.
You're a bit scary, so I prefer. You're less scary, so I prefer this. The average scariness decreases if you stay.
Defect.
I guess it's okay to just leave it on.
Okay. Everybody's ready. Are you ready?
Then nobody wants to get in. So everyone disappeared.
Yeah.
No, you don't. You.
That's
That's yours.
questions about the assessment report.
So I'd like to ask my question again, to see why.
Oh yeah, we skipped that question.
Why, I think it may, maybe it's gone, it's on the other board. Why?
Oh, is it still on the board? Oh, I don't think it is.
Okay,
There's
so
some more space up here.
It was why S with whatever you're calling the Euler class of the reduced regular representation.
Yeah, I think I called it
Why
alpha.
that isn't the infinity G.
So, okay. First of all, the right-hand side does not have fixed points. And I want to see that this map is non-trivial. So I claim that this map or this class is not zero in here, by minus whatever. But I claim that as soon as you restrict to any proper subgroup H, this becomes zero. So this map becomes null homotopic. And then in particular you kill all the lower fixed points except for the top group. But then if you look at these norm maps in G1H, you see that this passes through the restrictions. So the left hand side is trivial. And then if you take homotopy groups of that, whatever you have will still be at least naive, will be enough to get ring structures on homotopy groups. And then you would have to find in homotopy groups a ring map from 0 to some non-trivial ring. Particularly it has to send 0 to 1, and that's impossible.
So I'm very happy with that. But you could also say you had a norm on the homotopy groups, and you could make the same argument there.
Right.
And that seems to imply the corollary very simply.
The corollary is a lot easier than the theorem, yeah.
But I mean, it's immediate from the existence of the what you call the Greenleaf's main norms. You reduce up and restrict down, you're supposed to get it.
Yeah. And if you look at Jesper's argument in the special case that he proved, it's a lot easier than all this theory that I set up before. But I think you cite the Hill-Hopkins result.
Yeah.
But even in that case, checking these conditions is a lot easier than in the general case.
I mean, there's both a existence and a, you have to see that they exist in all these cases and they don't exist in other cases, right?
Right.
These are separate issues.
Very good, because I'm happy with that.
So do you know what happens if you take the free infinity, take a free infinity cell?
What do you mean?
Do you know what if you get these sorts of what the splitting looks like if you take a, or if you have a splitting like this, if you take a free infinity or free infinity cell instead of what spectra you studied and use the.
No, I haven't really thought about it. You're just thinking of the sort of the commutative algebra for an infinity.
Yeah.
I haven't really thought about it.
Another question: what happens on the modular categories?
That's a good point. This is basically your result. So of course, if you have any G-spectrum X and view it as a module over the sphere spectrum. Do I have to say why, or is that?
No.
Okay. And then the splitting of the sphere spectrum induces the splitting of this category into modules over all the idempotent summons. So this splits up into just the spectra X meshed with the local sphere. And then you can ask, what are the implications for multiplicative structures on these module categories? And it's essentially your result together with my kill that you get norm functors for exactly those norms that you still have in the local sphere. Norm functors from modules in H spectra at the group H up to G and so on.
Yeah, I might have one or two more. Do you have any other?
No, you go ahead.
Yeah, so can you say anything about what happens in, instead of restricting to G finite, if you take, say, S1?
I wrote this little section as you this about compact Lie groups.
I have to confess, I don't remember what you said, so.
No, okay. No, it's perfectly fine. I didn't work this out. I guess the main problem is it's a little bit harder to work with considering in this case, but I think that's possible. Maybe say a little bit about this. It's much harder to define it. And define it. Some compact Lie group. Take this one for now. Okay, this is a trivial example because I think it's just C. Say G is this general compact Lie group. You can define this by looking at Euler characteristics of finite G sub W complexes or whatever. And there is a classification of the idempotent elements similar to that of Trest that was done by Tom Dieck. You have to be a little bit careful because what you get is sort of extra topology, the idempotents. So if you take stack of this and you model out by identifying things in the same connected component, and you get a homeomorphism to the space of conjugated classes of perfect subgroups, where here the topology comes from the Hausdorff topology on G, and perfect means the torus extended by a finite perfect group.
And you mean you collapse the connected components?
Exactly, yeah. But it's still not a discrete space in general, because connected components are always closed, but they need not be open. So there are some point-set topological subtleties here. You have to figure out what the idempotents are, and they will correspond to the open and closed subsets. In particular, the primitive idempotents correspond to the open and closed connected components. So that's a bit more subtle, but you can look at this and you can just take some L where there's no problem, and you can still get a spectrum of this form. You can't call it an idempotent summon anymore because you don't have a decomposition of one anymore when there are infinitely many idempotents. But then you would have to rerun all this Hill-Hopkins machinery and I guess a little bit of your Gill machinery. And I don't think this has been done for non-finite groups. I guess it's going to be a bit harder because you might have to look at topological categories at some point and so on, enriched functors. I haven't tried to work this out. But of course the expectation is that my main results are still true for all finite index norms. But you can't do anything for the dimension shifting ones. So this is what I would expect.
Yeah, so are we allowed to talk about this? I mean,
I
so
think it's
I've
supposed to be
forgotten
discussion.
your, so to see that the the big extent infinity operator, which acts on EL on this thing, is easy using the algebra. Well, involves the analysis of the algebra. But then you have another argument to show that when they do satisfy that condition, you can have an action of that operator. That comes from the classification of and construction of all the infinity operators. Then.
You see that you do have an action
Yes.
if the conditions are satisfied.
Yes.
So I guess in the approach that I'm using this result by Gutierrez and White, which is a very general result that just says when certain localization functors preserve operatic algebra in that generality.
And does that generality apply to compact Lie groups?
As soon as you set up good model categories of categories of algebras over an infinity operator for compact Lie groups, then it's, I think from then on it's formal, but that might be the hard part.
It would be fun to do it for some, just rationally, for a few small compact Lie groups, but maybe not that.
Absolute thing.
Okay, so I also have a question. So these equivariant spectra that you have considered are all split in the sense that the G-fixed spectrum contains the underlying spectrum. Have you thought of examples that are not split?
No.
So the simplest example is KUR, but I don't know that the group is so small, so maybe there's nothing interesting to say. Another example is THH of anything.
I guess THH would be a very interesting example, but you would probably have to restrict the class of rings. You would have to make sure that whatever ring you start with as input, the classification of idempotence of THH of that ring is sort of tractable. I don't know if there are results along these lines. I think for some nice classes of rings, there's a relationship between the Picard group of the ring and THH, or I naught of THH.
The Picard group of what?
Of the ring you start with.
I doubt that.
Are you speculating that this kind of phenomenon depends on this thing being split?
It's just, it's non-split examples are typically more interesting.
Nonsense.
So what would be the easiest non-split example? That
Well,
would be
it's
this one.
KUR, but I don't.
Or non-equivariant cohomotopy.
What?
Non-equivariant cohomotopy. G plus is the representing ring.
I see.
And it's horrible, but
So just the orbit G plus. Of course, you could ask the same question for, or you could consider, so I wrote X over there as a module, you could consider all the orbits, G mod H, for example, as instances of X, and try to write down what the splitting is. Just as a
modules,
module.
yeah, that's quite interesting.
What if you take norms of things? Do you understand how this maybe this is a stupid question, but do you know what the idempotence, if you take the norm of a, if you take an infinity ring and you say over C2, and you, but then you norm it up, you'll get an infinity.
You're asking what the idempotents are?
Yeah, do you have control on that? Do you know?
I don't. So it relates to your question about the free kind of.
Yes.
It's a similar question. Yeah, I guess there's still some work to be done about the behavior. These are important fittings under restriction and norm, and also transfer, I guess.
I think that's enough.
Yeah.
You have more.
I don't have more.
So,
Probably is done.
yeah.
Okay, then. Yeah. Question? No. We.
We have to have a
You have to have a conversation.
Yeah, maybe we should try it.
Yeah.
Then should we
Turn off.
turn off the recording equipment and then
How do I do that?
I would.
I'll go over and try get
Press
the
the